And welcome back, students, to our next video with the LC3. We're continuing the ISA, and we're going to wrap that up today. So let's jump right in with control instructions. These are used to alter the sequence of instructions by changing the program counter, or the PC, as we've heard often. Conditional branch. This is a branch is taken if a specified condition is true. The signed offset is added to the program counter to yield a new PC. Else, the branch is not taken, the PC is not changed, and points to the next sequential instruction. Now, unconditional branch or jump always changes your program counter. There's no if then, it just is always going to change it. And lastly, you have a trap, which changes the program counter to the address of an OS service routine. Routine will return control to the next instruction after trap. Next up are condition codes. The LC3 has 3 condition code registers. N, Z, and P are for negative, 0, and positive. This is set by any instruction that writes a value to a register, whether that's AND, ADD, NOT, LD, LDR, LDI, and LEA. Exactly one will be set at all times, based upon the last instruction that altered the register. Let's talk a little bit more, though, about branch instruction. Now, a branch specifies one or more condition codes. If the set bit is specified, the branch is taken. So if we're looking at PC relative addressing, it means the target address is made by adding the signed offset, so IR8-0, to the current program counter. Now note, the PC has already been incremented at this point by the fetch stage. So the PC is already incremented, so it's never going to be at 0. So it's already started its process. Also note that the target of the branch instruction must be within 256 words of BR instruction. And BR, of course, meaning branch. If the branch is not taken, the next sequential instruction is executed. So here's our branch based upon PC relative instruction. And you can see with branch, our opcode now is all zeros. Yay, we finally get to see what all zeros represents. All right, and if we follow our diagram, we're starting first with the program counter here. All right, and that's feeding down into this AND. And of course, you also have the instructional register feeding out here. And also, you notice at the same time, this is feeding into these logic here. Right. Then this AND is going here into the mux. At the same time, the logic gate is also going forth here and feeding into the mux. Both of these then feed out here into the program control. So what happens if the bits 11 through 9 are all 0? So notice you have 11 through 9 are all 0. Or if all are 1. So if for some reason these all get set to 0 or they all get set to 1, if it's all set to 0, no CC is tested, so the branch is never taken. So pretty much it's just saying if it's false, don't do anything, just move on with your life. If all are 1, so if each one of the conditions is 1, then every single condition will be tested. All right, since at least one of the CC bits is set to 1 after each operate load instruction, then the branch is always taken. And assume some instruction has set CC before branch instruction, otherwise undefined. So it's kind of similar to like what we've seen with AND OR gates. If everything is false, if everything's zeros, it just cuts right out there. If everything's 1, it's going to go through each of those conditions. All right, using branch instructions. So in this example, I'm going to compute a sum of 12 integers. All right, so the numbers are going to start at the location 3100. The program starts at location 3000. So it's going to say, hey, store in R1, register 1 has this location 31,000. Register 3 is 0, and register 2 is 12. Right? And that's going to go here to ask, is R2 equal to 0? So here inside this operation here, it's going to say, you can see we multiply R1, store in R3, and take R3 plus R4, store in R3, R1 plus 1, store in R1, R2 minus 1, store in R2. That, of course, goes in here. All right. If it's a yes, it moves on. If this R2 does not equal 0, it's going back into this loop. Right? Because pretty much what we're looking to see is 12 integers. After you do what this does is after you have 12 integers, the program stops counting. Alright, but enough of that one because that might be a little confusing for you. Let's just move on to our next register, which is the jump register. Jump is an unconditional branch, which means it's always taken. Right. The target address is the contents of a register and allows for any target address. If you look in here, jump is 1100. Alright, we don't have to worry about any of that other stuff that we saw before here. You can notice these are all zeros, and that's because this is always taken. So with a jump, you go from your register file right into your program control. Alright, and lastly, let's just look at trap, which calls the services routine identified by 8-bit trap vector. And you can see trap now is all ones. Alright, so we've seen in this lesson we saw the all zeros, and now we get to see all ones. Right. And in this vector, you have in this you have three of them. You have x23, which inputs a character from the keyboard. X21 outputs a character to the monitor. And x25, which will halt the program. Right. When the routine is done, PC is set to the instruction following trap. And we'll talk about how this works later on. Here's another example. Right, let's count the occurrences of a character in a file. So the program again begins at location 3000. We're going to read a character from the keyboard. It could be any character. Then we're going to load each character from a quote file. A file, of course, is a sequence of memory locations. Starting address of file is not located, but stored in the memory location immediately after the program. If file character equals input character, we're going to increment the counter. So pretty much what that says is like, hey, since we're looking for the letter lowercase a, and in this program file, I just found an instance of it. Oh, well, that means there's at least one. And then when it goes to the next character, it's going to make it 2, and then 3, and then 4, until it reaches the end of the file. Now, the end of file is indicated by a special ASCII character value. We have T or X04, so that's pretty much end of the file. At the end, print the number of characters and halt. Assume there will be less than 10 occurrences of the character. Now, that special character that's used to indicate the end of sequence is often called a sentinel. And you'll hear that term used across different programming terminologies. Pretty much the sentinel is just used to indicate the end of the file. All right, and the sentinels are very useful, especially when you don't know ahead of time how many times you're going to need to execute that loop to find where the end of the file is. So here's a quick flow chart. And you can see here I'm using a count function, so I'm going to see it when count is 0. So count is 0 or reg 2 is 0. So then I'm going to use PTR for its file character, and then you can see we then get an input from the keyboard. We load that character from the file. From there, we ask, are we done? There we go. We're going to go see if they match. If it does match, we increment. If no, we're going to load the next character from the file. Either way, we're going to keep going and do this loop here until we find out that that program is indeed done. Once that matches the end of the file, it's going to say yes. It's going to convert the count that we have stored up into an ASCII character. Then it's going to print out the count using trap here. And then lastly, we're going to halt the function here, halt this program, because at that point we're pretty much done. Data path components. All right, little things to talk about here. We have a global bus. This is a special set of wires that carry a 16-bit signal to many components. And inputs to the bus are, quote, tri-state devices. Quote, that only place a signal on the bus when they are enabled. Now, the key thing to note here is that only one 16-bit signal should be enabled at any time. The control unit decides what signal drives the bus, so to speak. Any number of components can read the bus, and the register only captures bus data if it is enabled by the control unit. So otherwise, the register doesn't really have any business working or looking at even the bus. Now, we also, of course, have our good old friend memory here. Memory can control data and registers for memory and I/O devices. I/O meaning input/output. Now, memory we've seen is MAR and MDR, which control the signals for read and write. Continuing on more data path components, we have the ALU, all right, that is our arithmetic logical unit, which accepts input from a register file. and from sign extended bits from the IR. Output would then go to the bus, which is used by condition code logic, the register files, and memory. Register files, these are two read addresses, S1 and S2, and there's also one write address, DR. You get an input from the bus, which is a result of the ALU operation or a memory read. And there's two 16-bit outputs that come from the register file. These are used by the ALU, the program counter, and memory address. And the data is used to store instructions passing to the ALU. PC and PC mux. There are three components to PC, which are controlled by PC mux. PC plus 1, which is part of our fetch stage. The address adder, which is for branching and jump. And lastly, but, which of course is part of trap, which we will discuss later. You have mar and mar mux. There are two inputs to mar, controlled by mar mux. You have an address adder, so that is your load and store there. And you have X0 extended, which again we're getting into trap, which we will discuss more later. Data path components. Still going here. Condition code logic looks at the value on the bus and generates NZ or P signals, so that's your negative, 0, or positive. The registers set only when the control unit enables them. Only certain instructions will be able to set the codes. So AND, add, not, LD, LDI, LDR, LEA, they're the only ones that can kind of set the codes into the registers. The control unit is a finite state machine. Remember we talked about that earlier, about the concept of a finite state machine. On each machine cycle, it changes control signals for the next phase of instruction processing. So who's driving the bus? Is it the gate PC? Is it the gate ALU? Which registers are write enabled? Is it the LD, IR, or LD, REG? Which operation should the ALU perform? And lastly, the logic also includes a decoder for the opcodes. Because otherwise, like, well, how do you tell what an opcode is different from another one? You have to have a decoder in place for that. All right, folks, this is kind of a lengthy one, but that concludes our notes for this lesson. Until next time.